Right. Right. Okay. Thanks, Andre. Right. So, welcome to this talk. Thank you for coming. I know it's the end of the day, but I'm really impressed at the number of people who turned out. And I'd also like to say thank you to the organisers for inviting me back to this amazing event. This is only one of the largest Java conferences in the Ukraine. I'm really impressed with what's going on in the Ukraine in terms of programming. So I'm here to talk about, well, as you see, algorithm performance in the new machine age. I'll start with a very short introduction to me. This is who I am, and these are, if you've heard of me in the Java world, it might be because I've written a couple of books. I wrote a book on Java 5 and a book on Java 8, and I've done these other things as well. But the reason I'm really here today is to talk about the consequence of writing the book on Java 5. So that was I wrote the collections part of that book, and the great thing about writing books is that you get a chance to talk about them. You get a chance to talk about them twice, actually. So first of all, you say, "Oh, I've written this great book, and it's got all these really useful things that you should know about in it." And then a few years later, you can go around and say, I wrote this book, and now I'm really sorry about all the things I got wrong in it, and I want to tell you about the mistakes I made. So I'm now at that stage for the Java 5 book. It's a long time ago. It's not so much that I got things wrong, but there's a lot of things that need to be added to what was in there. So one of the things that the thing that I'm mainly talking about here, obviously, as you know, is about algorithm performance, and I'm going to talk about time complexity. This is the kind of common phrase that was used for a very long time, certainly when I was learning about computing, and for many years after that, as a measure of how fast a program would execute. So the idea of time complexity is, it has formed a mental model of program performance for us for all these years, and basically it depends on the idea is that a program, the cost of executing a program is in some way correlated with the number of instructions that are going to be executed. And that seems intuitively like a pretty sound idea. I mean, we know that programs actually do their work by executing instructions. So presumably the more instructions that are to be executed, the longer the program's going to take. And this model was a really good one for quite a long time. And I'm going to explain the reasons why it was a good one for a long time and why it's not adequate now. So why we need to change it. So since the talk is entitled "Not Your Father's Complexity," and maybe I should say there's a phrase in English which maybe isn't so familiar to non-native speakers. Which, if you say "not your father's something," it means not the thing you were brought up on. So, like, it's not what your father learned. So, it's a reasonable question to ask. Well, like, who is your father in that case? Well, I mean, that's not a biological question. I'm not asking a personal question here. In terms of what you know professionally about time complexity, it's this man. So Don Knuth, a giant figure in the world of programming, creator of tech, Turing Award laureate, and a whole lot of other stuff as well. And primarily for what we want to talk about here is the author of The Art of Computer Programming, which is this multi-volume. Oh, it's gone. This multi-volume work in which he analyzes algorithms. Like that. In which he analyzes algorithms and, in particular, does a lot of foundational work on time complexity. And so it derives, and the opening slide, which you saw at the beginning there, which has actually been enough to drive people away from this talk, even before I opened my mouth in the past. But luckily, I'm not going to force you to understand the kinds of things that are written on there. But that's a screenshot of one page taken from, I think, volume 2 of The Art of Computer Programming. So, before I go on to say modify the things that we need to learn about time complexity and move away from Knuth's foundational studies, there is something I should say about this, and that is that we really spend far too much time thinking about this. And Knuth knew that as well, even though he spent years thinking about time complexity. He also said this. And you don't need to read the whole this first paragraph. You just need to read what it says there. We should forget about small efficiencies, maybe 90%, maybe 97% of the time. That's a figure chosen pretty much at random, but it's a very high figure. And the idea of this is that what is more important than program performance nearly all the time is are the other virtues of a program, so that it should be readable and it should be maintainable. It should be in a style that everybody's going to be able to understand very easily. It should be often scalable. We may care about that more than the individual performance of individual components. So everybody focuses on performance. Everybody's kind of hooked on it, and I admit I am as well. I'm here talking about it, but it's much less important usually than people think in everyday life. So I always have to say this at the beginning of every talk that I give on performance, and then I go on to talk about performance. But we should bear it. We should bear it in mind. So question is, before we go on to say, well, what more do we need to do besides think about computational complexity? Let's think about what time complexity is. Well, it's a pretty simple idea, even though if you look up the definition of it, it'll look hard, and I'll make it look hard by giving you the definition. Actually, it's very simple. It's a bounding function on the number of steps that a program's going to take to execute. So an algorithm with time complexity, and typically it'll be something like order n, or order n squared, or order n cubed in a bad case, something like that. It'll complete in less than something like that number of steps, that function of steps, provided you can define a multiplication factor and a lower bound above which it'll always be. So here's a picture of it. Here we've got an algorithm which executes in some number of steps. We don't know how many. The size of the data is along here. Here's the number of steps, and you don't know what exactly. It's very difficult often to find the exact number of steps an algorithm's going to take to execute that f of n. But provided you can find a g of n and multiply it by a big enough number, then above this number k, this threshold k, this will provide an upper bound for the number of for the number of steps it'll take to execute. So here's an example, a very simple example, I have to say, chosen from the sorting and searching volume of The Art of Computer Programming. From multiple list insertion sort, the number of steps it's going to take to execute is 3.5n squared plus 24.5n plus 4m, where m is the number of lists, and n is the length of each list, plus 2. And that's the number of steps it will take. Actually, so Knuth spent a lot of time thinking about this. This is, and time complexity is a fantastically interesting subject, time complexity analysis of algorithms. But actually, you don't really care very much about this. The only thing you really care about is the n squared term. Because for a sufficiently large data size, it's that term that's always going to dominate. And so actually, in the limit, it's the effect of doubling the size of the list in the multiple list insertion sort is going to be to multiply the number of execution steps by 4, because 4 is 2 squared. So you double the data size, you're going to multiply it by 4. And that's really the most important thing you need to know about that. And actually that enables you to classify virtually all the algorithms that we're interested in into a very small number of time complexity classes. So the ones we're really interested in are the ones that are in this table. Even though there's infinitely many of them, and it's the study of these infinitely many time complexity classes has formed the basis of innumerable papers and PhD theses and textbooks. Actually, we're really not very interested most of the time, except in really the first 4 of these. So if you double the size of a constant time algorithm, if you double the data size, it won't change the execution time. And that's for example, if insertion into an empty hash table. If it's log n, it'll be increased by a constant. So that's typically binary search. Double the size of if you double the size of a data structure you're searching by binary search, you'll increase the number of steps it needs to take to locate your element. You'll increase it by a constant, because it's got to divide it once more, and so on. Linear is doubled. N log n, which is typical for sorting algorithms, is doubled plus an amount proportional to n. And past that, you actually really don't care, because those algorithms, any algorithms that have n squared or above, are typically not feasible for large data sets. So that's the kind of background to why we're interested in the time complexity of algorithms, and really that's really all I want to say about this, except how it applies to collections in Java, which is something like all Java programmers have to know about and have to deal with it all the time. So when I wrote the Java 5 book on collections, what I wanted to do was to say, like, which collection should you choose? How should you decide what collection you're going to use for your particular problem? So another candidate for your father in terms of your professional father is somebody whose work we use literally every day as Java programmers, and it's this guy, Joshua Bloch, who is the author of Effective Java, and therefore very well known for that, but also the author of the Java Collections Framework, the original author of the Java Collections Framework, which came out in 1998 with Java 2, and therefore really sort of set the foundations for the way almost all Java programmers work all the time. So when I wrote the book, when I wrote my section of the Java 5 book, I had the fantastic good fortune to have him as a technical reviewer. This transformed the quality of the book from not very good to really reasonably adequate, because his review was so extremely thorough and helpful, and by the way, extremely severe. So, like, a typical comment from Josh about some minor mistake I've made is, "This is totally wrong and misleading." So that's him at at about 5 on a scale of 0 to 10 in terms of criticism. But it was really, really useful to me. And one of the things he told me was, I had good diagrams like this in the book before he shook me up, and you will still see these in many textbooks. And the material in here, it shows you the interfaces. It shows you these interfaces, and it shows you lots of abstract classes. And he said, don't talk about the abstract classes. They are no relevance to the client programmer. What the client programmer wants to know is what are the interfaces, and what implementations are there? What concrete implementations are there available for those interfaces, and how are you going to use them? So the Java Collections Framework is interface-based. You should choose the interface that you need according to the functional requirements of your program. This doesn't work so well for some things. I mean, like, for queues, it's not exactly right, but this is certainly how it started out. And then you look at the typical usage scenario of your program, and you decide on the basis of how it's going to be using the data structure which implementation you should use. So, for example, if you've got an algorithm which is going to be adding and removing elements from the beginning of a list, from the 0th element of a list, then in principle, array list doesn't look like a very good choice, because if you add an element at the start of an array list, or if you remove one, you're going to have to shuffle all the elements in the list up or down, according to whether it's an insertion or removal, because of course array lists are always 0 indexed. So it looks as though what you should do is choose a linked list for a problem like that, because that only requires you to do some pointer switching. You have to create or remove a new linked list node, and then you have to switch some pointers around, and it should be order 1. It should be constant time. So your choices then, if you need to use a list, is which implementation of the interface do you require, and it's going to be actually it's quite limited in the Java Collections Framework. It's really between array list and linked list, but also there's a copy on write array list, which is useful in some cases. So the collections chapters in the Java 5 book have got various tables in them like this, which will tell you, depending on which operations you've got to do more of, which implementation would be better. If you're doing lots of remove zeros, then array list is bad, whereas linked list is good. That's what this table tells you. And similarly, if you're doing a lot of gets from random positions, from arbitrary positions in the list, then an array list is good because it's got random access, and a linked list is bad because you're going to have to step through the structure in order to be able to find the element you want. So did this ever make sense? And the answer is, well, yes, it did. I mean, it wasn't a bad idea on some assumptions. So the assumptions it depended on was obviously that you can ignore constant factors. So basically, order 1 just tells you that the number of execution steps is going to be proportional to the data size, but it doesn't tell you what the constant of proportionality is. And that could be really important if, for example, the operation is intensified. So actually adding and removing elements from an array list turns into an array copy. An array copy is an intensified operation, so that in fact it's really fast. Yes, it is still order n, of course. Magic isn't done, but the constant of proportionality really does matter. There's an assumption that all instructions have the same duration. It doesn't. Time complexity calculations don't take that into account, and we know that in fact divide is an order of magnitude slower than addition. There's an assumption that memory doesn't matter, and memory actually, it turns out, really does matter a lot for us in these things. I'm going to go on to talk about that. There is a concept of space complexity as well, but that doesn't usually enter into these calculations. And also, and this is really important, that instruction execution is the thing that actually really decides how fast a program is going to run. Now, let's say that it's actually the operation by the processor of carrying the instructions out, which is going to take the most time. Well, why would that not be the case? Well, the answer is that modern machine architectures mean that actually instruction execution may well not be, and it often isn't, the biggest consumer of time. So complexity study was definitely worth it, even though, of course, we knew that, the kind of standard caveats. Of course, we knew that there are many other bottlenecks in the execution of a program. So there's all the stuff that I've got on there: disk and network, overheads, garbage collection, resource contention. All of these things. I'm not going to talk about these here, but if you want to use what I'm saying in this talk as a way of understanding program performance, then you've got to understand it. Yeah, it's real, but it's obviously only one factor. These other factors here are very important too. And the standard thing is that the standard performance tuning metaphor is that you've got a pipeline of, if you conceive of your program as being kind of workflow execution, then if you remove one constriction, the bottleneck in the pipeline, the idea is, well, that's going to mean a greatly increased flow. But in fact, it may turn out you've got another bottleneck further downstream, which in fact will perform worse as a result of you releasing the constraint further upstream. So the complexity study was worth it, but the thing that has really changed has been machine architectures more than anything else, and they've actually changed the whole way we should be thinking about performance. When I learned about how computers worked, which I thought was going to be unchangeable, and it was pre-1980, because you can see how old I am. It was a pretty easy model to internalize. You had a CPU, and what it would do would be it would retrieve the CPU would retrieve instructions from the memory unit using the program counter, and it would use those. It would send those to the ALU, the arithmetic logic unit, which would either get data from an input device or also from memory, do the operation and send it to the output device. And this seemed like a pretty simple model that you couldn't really go too far wrong with. I couldn't resist, when I was preparing this talk, looking for pictures of pre-1980 machines. So this is what they looked like, and I like showing this because sometimes somebody says, "Oh, that's a machine hall." Can you imagine when you had things called machine halls? There was giant rooms. I remember the first serious job I had. The machine hall was maybe about the width of this and about 3 times the length of it, and it was full of machines. And these machines they all looked like this, big cabinets. And I imagine probably the power in one of these sets of cabinets, it was going to be much less than the mobile phone you're carrying in your pocket. And I have to add as well that if you look for the adverts for programs, the other thing that I found when I was searching for images of pre-1980 computers was that all the not mainframes like this, but they had something called a mini computer. And mini computers were often advertised. There was a sort of mid-range capacity below the mainframe that you see there, but above the kind of microchips that we had in those days. And the way that they advertised them was always they would take pictures of them in the garden. I really don't. I don't know why, but for some reason they were thought to be much more picturesque out there. And there was always a compulsory element in these adverts as well. There always was a woman in them. And usually, I mean, I had to search quite a long time to find one where the image was one that I could safely put up in today's environment. And things have changed really quite a lot in many ways, not only in terms of machine architecture. So what happened to, what's the big change that took place since 1980? Well, I titled this slide, it should be the golden age of complexity analysis. The biggest thing, a very big thing that happened was that between 1980 and 2010, the cost of DRAM went down like this. And this is a massive decrease. To give you an idea, I could say that in the 1970s, I can't remember the exact point in the 1970s, but I did find this. The typical cost of DRAM was $1 per byte. You just imagine that in terms of the size of the memory that we expect nowadays. So what happened was that the dominating factor in program performance changed. I mean, prior to this massive decrease in the price of RAM, it was far too expensive to afford on a large scale, and so what would happen would be that people would always the Knuth's books are full of what do they call them? External sorting algorithms. So external sorting was a big thing. No, hardly anybody's heard of it now. External sorting is when you can't get your data structure you want to sort into memory all in one go. So you've got to keep on swapping it section by section from disk. So it's quite clear that for an external sorting algorithm, although the cost of program execution may be quite interesting, actually the thing that's going to dominate performance is how fast your disk is, because you're shuffling stuff backwards and forwards to disk all the time. So paging costs are going to dominate. And as the cost of memory came down and the size of memory therefore went up, you got the golden age of complexity analysis. Magic. It's cheap enough now to execute algorithms in memory. So internal sorting, as they called it, became the thing. And you know, you think, well, now we understand. Now we've got a real handle on how much programs are going to cost to execute, because they're going to be working in memory all the time. But something went wrong. What went wrong? What happened? I mean, it's not like the cost of memory didn't continue to go down, and continues to go down. So what happened was this. That while the cost of memory was going down like this, something else happened. Well, the performance of memory went up, which is really cool. So it went up by a factor of 10 over 40 years, which is kind of great. But the performance of processors went up dramatically. And that's really the thing that has completely governed not only the hardware architecture since, but what we need to, how, for example, all the problems we have with concurrency. The Java memory model depends entirely, or rather, is designed entirely to cope with the problems about how do you bridge the gap between the speed of the processors, which is incredibly fast now, compared to the speed of memory. And the problem is you can't get the data and the instructions fast enough up from memory to keep the processors busy. And all the ingenuity of the hardware architects has been spent in trying to work out how to bridge that gap. So the big question that faces them, more than any other, there are many of course, but the one that faces them more than any others is how to keep the cores running, how to keep the cores hot, supplied with data and instructions. And the answer is you use a lot of cache. So in a modern chip, anything up to 80% of the real estate of the chip can be given over to cache. And the cache is in several levels. There's this thing called the memory hierarchy, which is like, the idea of it is that you've got relatively slow cache, but with high capacity faster, but with a lower capacity, because of course it's more expensive. Very fast. Keep it close to the processor. Often the memory hierarchy is shown with a diagram like this, and there's a very clear trend. As you go up the memory hierarchy, you get stuff nearer and nearer to the CPU. The speed of it goes up, the power it consumes goes up, and the cost also goes up. So as an advantage, the cost is obviously highest. The cost is lowest for the last level cache, or back, down to disk, where storage costs almost nothing at all. And now there's a big issue here because this whole question about how the memory hierarchy works depends on the fact that the idea is that you've got this chain of, I mean, on this slide you've got this chain of caches, these 3 caches, and there's you can think of it as a pipeline that keeps as a processor requires data, it makes its way up through the caches, and keeping that pipeline fed is really critical to performance. So an example of the kind of problem is on my MacBook Pro here, mid 2014. 13, it's 3 gigahertz Intel Core i7. It's got, it doesn't matter how big the caches are, we'll come on to that. Since it's 3 gigahertz, one cycle in memory is about 1/3 of a nanosecond. Level 1 cache is 1 nanosecond, level 2 cache is 4 nanoseconds. So we're going up by a factor of 3 or 4 as each level as we go down. Level 3 is 16 nanoseconds. And main memory is more than 100 nanoseconds. It's more than 300 times, it takes more than 300 times as long to get data up from main memory as it takes to execute the instruction or execute an instruction on the data once you've got it there. So it's a massive difference. And the result is that if you, what's the time? I'll do it. So sometimes I use the analogy, because you're thinking like, I know everybody's saying 100 nanoseconds, that's really not a very long time. So to turn it into units we can understand, I like to use the analogy of a cook standing at the cooker. Pardon? Yeah, right. 20 minutes to go, yeah, okay. Boiling eggs, thank you. Boiling eggs, and each egg takes 3 minutes to boil. So they take an egg from the hands. I mean, my other picture for this is something like this. So it's like a bucket chain where you've got things are being passed. A Mongolian stamp of 1977 about how you put out fires in Mongolia when you don't have. So buckets, the data's being passed up there, and the guy at this end supposing he's going to take 3 minutes I'm confusing myself. So because you pushed me on the time. So the idea is that if it took you 3 minutes to boil an egg at the cooker, that was handed to you by the next guy in the chain, then provided you keep on being supplied, you're going to be able to you'll be able to keep the cooker in use. If for some reason that chain breaks, as could happen, for example, if there's a cache miss and the data has to be retrieved all the way from main memory, it's going to take about 300 times as long to get the data from main memory as it takes to get it from as it takes you to do the cooking. So 300 times 3 minutes is 900 minutes, about 15 hours. You're going to be drumming your fingers on the cooker for about 15 hours waiting for the egg to come from the fridge, as I like to say. And if instead the fridge is empty because main memory doesn't have what you need and you've got to go out to disk for it, it's going to be another 300 times as long as that, roughly speaking. So we're now talking about, instead of 15 hours, we're talking about a year or 2 years or something like that to go to the shops to get the eggs. That's how long the processor will be standing idle. So cache effects often dominate the performance of programs. And I think I've probably said all of this stuff. Well, yeah, but I mean, they've worked really, really hard on this. The hardware architects are very ingenious. Typical programs have a 95% hit rate. So you think this is brilliant, but the other 5% really hurts. It really it can dominate the performance of your program. What are the reasons for cache misses? Well, there are 2 possible reasons. There are many others, but I'm going to talk about 2 here. There's a cache capacity issue, and there's a failure of prefetching. And I'll look at both of these sort of relatively quickly, I hope. So first of all, let me explain. Everyone will understand with the issue to do with cache capacity, because like the cache isn't big enough, and there's reasons both of cost, of power, and of also of real estate why caches can't be made arbitrarily big, tempting as that is. But the way that prefetching works needs a bit of explanation. So the idea of prefetching is, if you've got main memory down here, and you've got a correspondence between different cache lines, each unit in a, say, level 1 cache, I'll just talk about that now, it's typically 64 bytes, bytes, and there's going to be, so you can imagine that each line in the cache corresponds to an area of memory. So this would be a 64-byte area. Now what happens is, what you want is to make sure that the cache is always full of data especially that the program's going to want. So how can that be ensured? Well, one really important way of doing it is what's called prefetching, stride prefetching. And the idea of this is that if the processor can observe that you've got a regular linear access, or I mean, it doesn't need to be here. I've made it as simple as possible. But the idea is that the processor is pretty good at observing patterns of data retrieval from memory. So if it can detect a consistent pattern, it will get ahead of itself, and it will retrieve data from there that it can tell is going to be needed. And if it gets it wrong occasionally, that's not the end of the world. It will be a cache miss, but provided but if the numbers are in your favor, then things are good. So what happens is it can tell, okay, this is the one I'm going to need next, and it gets this up there in advance. So of course, in an object-oriented program, and with the collections that we normally use, but actually with object allocation generally, we don't get that, because of course all of our programming is pointer-based. We're allocating new objects, and the pointers and where they are in memory is not under our control. So actually what happens is that most of the time, not when we're accessing primitive arrays, obviously, but when we're accessing data structures, we're all over the place in memory, and we completely frustrate stride prefetching. There's an additional problem as well, which I'm not going to go into in a lot of detail here because I'm running short of time. But there's also an additional problem is that memory is divided into pages. The processor deals with virtual addresses, which have to be translated into real physical addresses. Now, I don't want to go into this in too much detail, but there's got to be a translation mechanism for doing that. So it's called a page table, but it sits in main memory. So you've got to cache the page table as well. It's something called a translation buffer. And if you jump outside of a page, then not only do you have to retrieve the data, but you've even got to find it in the first place. And if that means actually refreshing a line in the translation buffer, that's 2 memory accesses, and that's twice you've got to wait for the eggs to come up from the fridge. So there's clearly this is a really important issue to deal with. So getting back to the main theme, I've talked about complexity, I've talked about caching. Let's have a look at how caching plays with complexity for actual collections that Java programmers might use, or data structures that Java programmers might use. So I'm just going to take a very simple example here, traversing a list. And obviously traversing a list, linearly traversing a list is order n, right? So it should be that if you double the data size, you're going to double the execution time. So let's have a look at, we'll compare a linked list and a primitive array. So here's the results from a linked list. So I got these results using JMH, the Java micro benchmarking harness, and I linked it up to Perf, the Linux tool that will allow you to actually look at the hardware counters, so we could actually see what's going on. And so here are the results for a linked list on a machine similar but not the same as this one. And we looked at it I looked at it for a linked list with 1K, 7K, 63, and 511, and the performance on the nanoseconds per operation is, as you can see, and an operation is regarded as being like stepping onto the next element of the list. And you can see that it drops off pretty dramatically, not so much from 1 to 7, but from 7 to 63, it's a big drop off, and from 63 to 511 also a drop off as well. What's going on here? Well, we can see this CPI, the clock ticks per instruction, is a measure that hardware engineers would look at in order to find out generally how healthy a program is. So it tells you the clock ticks per instruction it tells you from a hardware point of view how fast, whether the cores are being kept hot. It's not only that, but that's the kind of primary measure of are the cores being kept hot. And obviously, they start off with 0.32, which is pretty good. It means that there's 3 instructions being executed for each clock tick. How's that being done? That's being done via instruction level parallelism. In other words, a different kind of pipelining, which I don't have time to talk about here, but that's a healthy number, and that's an unhealthy number. All right, so that's the baseline. Here's an interesting thing. This one's not so interesting. The cycles per operation. That goes along with this. Here's the interesting thing. The number of instructions, the number of machine instructions for each operation is absolutely constant. So that tells you that it really is order n. The number of instructions that are being executed is not varying according to the length of the list. Something else is going on. So what's the thing that's going on? The thing that's going on is the number of level 1 load misses is going up. And it's gone up. You can see it's increasing quite a lot. It doesn't look like very many. There's not that many load misses, and it's not increasing that much. But remember that I said that the very few cache misses that you get have a huge disproportionate effect on your program performance. And the level 1 cache loads are going up as well. This doesn't account for everything that we see here. In fact, if we go down to the bottom, we can see the last level cache, which is the bottom one nearest to the memory, is also starting to get cache misses at the end here, and that's going to be very expensive as well. And that accounts for the increase between 63 and 511K. So you can see that the load misses are starting to be quite significant there. So it's a very dramatic deterioration in performance for a relatively small increase in the number of cache misses. It shows how important that is. Okay, so. I'll skip over the rest of that. So what's going on? Well, the linked list, the node size of a linked list is 24 bytes because it's got a backward pointer, it's got a forward pointer, and it's got a pointer to the data that it's storing, and it's got the usual 8-byte header that any object has. So you add all that up, and you get 20 bytes, and then it's rounded up to 24, and you've only got 32K in the Core i5 on which that was running. So it's pretty clear that straight away you're going to blow the size of the cache. I mean, for 1K for the 1K linked list, you're going to blow the cache immediately, and from then on you're just reloading it all the time for all the iterations. So it's simply a matter in this case of cache capacity. And surprisingly, an array list is only going to be a little bit better not because of course the array list is much better in terms of the capacity that the data structure uses, but because if it's an array list of integer, and we have to have integer because, of course, our collections only can point to objects, then in fact each new element costs 20 bytes. But that's 4 for the pointer in the array, the array of pointers, and 16 elements for the integer. So actually, you're not that much better off. Okay, this is 40 and that's 20, but you're going to blow the cache for only twice as many elements. So it's still pretty bad. Let's look at the same thing for a primitive array. If we iterate over a primitive array under the same conditions, we get completely different results. And I bring the same things in red again that we had before. The CPI just stays the same. I mean, of course, if we made the primitive array big enough, then that too would blow the cache. But you can see how much bigger it needs to be. The instructions, the CPI is the same. The instructions are, of course, the same. There's virtually no cache misses here. There's no cache misses on the last level cache at all. And so the performance is genuinely completely linear. Completely linear, and this is an issue. This is a straightforward issue of just like if you can't cache efficiently, then you're just not going to be able to get good performance. And you can see how much the performance deteriorated for linked list. Poor old linked list. Nobody loves it, but for that reason, basically. Okay. Second issue is the second issue is data locality. So I've talked about cache capacity. Now I'm going to talk about data locality. You saw the way that the stride prefetching worked. Now I'm going to see how much. There are two different problems. One of them is, can you actually make sure that your cache lines, your 64-byte cache lines, really contain the data you want? Because if they're mixed up, if the data in the cache lines is mixed up with stuff that from other programs, you may be needing to reload a cache line very frequently. I mean, like instead of being able to use the whole of your 64 bytes, you may only be able to use a relatively small amount of it because the rest of the cache line actually is required by data for other algorithms. So this is an issue which I'm not going to talk about except in passing here. But let's just take a quick look at the problem of prefetching. So I did an experiment here, and I populated the linked list in two different ways to see what would happen. I populated it in what I call a natural way, and the idea of this is, I mean, this is just my phrase, and basically the code is this, and I'm just creating the nodes and effectively alternating the creation of nodes with the creation of the allocation of memory for the data. So it's going to be relatively compact. I've tried to make sure of that. And then as an alternative to that, I've populated linked lists in a random way, which so the idea of that is I've first of all created an array list, and I made sure that the array list was going to be pretty big, and I allocated the integers. This is really all I'm interested in, the integer objects. I allocated them in a way that's going to make sure they're pretty much contiguous. And then what I did was I got elements from the random position and put them into the linked list. So now the linked list is pointing randomly. Each of the different elements, instead of being predictably constructed, are pointing to wildly different places in this array. So that's the idea there, and now I run the experiment, and because every talk ought really to have a demo, here's the demo. But because you can't do a performance test during a talk, I've tried it, and really the results you get are just not at all brilliant. What I did was I recorded a performance test and then speeded it up a lot, so that I only have to keep on talking now or juggling or whatever it is that we do for a couple of minutes while this is going on. But you see, this is what a JMH test looks like while it's executing. I mean, this one probably took about well, you can see it only took 5 minutes, but 5 minutes is far too long to spend when you've only got 6 minutes left of your talk. So you might be wondering, well, what can we do about all of this? I'll fill in the time while the test is running. What can we do about all this? Well, the answer is, I think that if you're conscious of it, there is a possibility of actually organizing your data so that it is more, so that it is nearer to being contiguous in the way that I've described. It certainly would help to be aware of that. I mean, there are possibilities. I mean, one possibility that I've considered, I haven't run any experiments, but I know it would work, would be to actually reorganize your data. If you had a data structure which was going to change relatively infrequently, then you could actually organize your data so that it would be contiguous. So here's the difference between in the performance between the natural and the random allocation. This is performance, and we've got 8 nanoseconds per operation for the natural allocation, and 28 for the and 28 for the random allocation. It's a big difference, and as you can see, the code is almost identical. You would not have been able to predict this if you hadn't had a mental model of what was going to happen. You'd have thought, well, like the code looks almost exactly the same. So this is why nobody loves linked list. Poor unloved linked list. Here's a tweet from Josh Bloch. He says, "Does anybody use linked list? I wrote it and I never use it." It's the least favorite data structure in the Java Collections framework, and the reason is because it takes up so much space. And I never understood why taking up space would be a problem until I looked at this stuff. So I'm near the conclusion now. I've got another. No more demos. I want to just emphasize that we may not be looking at the right thing when we try and imagine what's going to be happening in our programs. With hash maps, everyone knows that the potential problem about hash maps is collision between the same hash code being calculated and leading a hashing of elements to the same bucket, and then you get overflow. I mean, the way a hash map is supposed to work is something like this. Another element comes in, and you get a how's it going? oh, that's right. So here comes another element, and it goes to another node, and this is meant to be constant time, right? And so you think this is good because, hey, constant time algorithms are really great, and you think, well, but on the other hand, if instead I get a HashMap collision, so it goes to the same bucket the second time, well, I'm going to have to form a chain. In Java 8 and onwards, you form a binary tree. But in any case, you've got linked lists. So you think, well, so this is going to cost more because you've got to traverse the linked list. But what I'm trying to get over to you is, although obviously this is worse, and you want to avoid it if you can, actually it may not be as much worse as you think, because even the non-overflow scenario still has you loading memory from random places, and therefore frustrating prefetching. So what's the way around this? Well, there's been a little bit of work Java 9 contains these immutable collections. So the idea of the immutable collections is that once they're created, obviously they'll never change. That's what immutability means. And the nice thing about that is that at least in the case of a map, for example, it's an array of pairs of elements. There's an internal data structure for pairs of elements, and it means that you can construct it like this. And if you manage to create all your data, supposing you could populate it in this kind of way, then it may, in other words, pointing it only at objects that you've created for the purpose of building the map, then you could get good contiguity. You could get your elements stored close together. Well, of course, you often won't be able to manage that. So one strategy might be, for example, if you had a map that you were constructing dynamically, but then you always wanted to use as a read-only structure, would be to actually copy it into an immutable map. And that would give you much better data locality and better performance in other ways. So there are various third-party frameworks that, the Java Collections framework, you can work around it in the kind of way that I've described. There are various third-party frameworks which try and solve this problem in different ways. So reducing memory footprint is a common aim of all collections frameworks. So it's much more important maybe than you thought. You thought that what the important thing was to reduce the execution time, but it actually turns out that actually reducing memory footprint is really important as well. So there's not really time to talk about the different aspects of these various collection frameworks, but to say that all of them make claims for reducing memory footprints. And there are performance comparisons. I've seen some very useful performance comparisons recently, but they tend not to focus on this particular issue. So there's more work to be done there. More work to be done by me. I feel like I would like to have more experimental results to present here. Improving data locality is a tougher problem because all these frameworks, or nearly all of them, depend on the basic idea of objects and pointers to objects. So data locality is a tough nut to crack if you stick within the way that we've been thinking about how to build data structures in Java. So there's a library called Object Layout which tackles this problem very explicitly. The idea of object layout is the primary thing that it provides is an array of like C-style structs. So it basically gives you exactly what you would hope to have in terms of absolutely contiguous memory and the data organized within an array. So you're going to get data locality, and you're also going to get extreme economy of memory of the memory footprint. Obviously, the downside of that is it's going to be immutable, right? So once you've created it, there's a lot of stuff that you can't do that you expect to do with Java collections. I've been told about roaring bitmaps, but I really oughtn't to say anything about them because basically this is hearsay. Project Valhalla has a very big objective, which will definitely help. Project Valhalla will solve some of these problems completely. It's aimed squarely at this difficulty. So this is a language-level solution, which will give you arrays of, which will allow you to have arrays of, collections of primitive objects, which is really what we want here. And it will allow you to have value objects, which will organize their data really like primitives, but will be equipped to behave like objects. So it will bridge the gap between what the programmer expects in terms of object orientation and what the implementation requires in terms of primitives. So Project Valhalla is definitely what we're looking for in the long term, but we don't know how long that term is going to be. With the new release schedule for Java is encouraging, but we still don't. They're never going to commit to something like this until it's much, much nearer. So my conclusion of sorts is that performance mostly doesn't matter, because I have to say this. I say it at the beginning, I say it at the end. But when it does matter, it really matters. So I can't get away with just saying, forget about it. Every performance improvement always represents a trade-off. So for example, you could have you get much better data locality if you have what's called open hashing, where the data for a hash table is actually stored within the bucket array. But there's a trade-off there. I mean, that will give you much better performance at low loading, when the table is lightly loaded. When the table is heavily loaded, you'll start to pay for that data locality with greatly increased search times. So every performance improvement represents a trade-off. Algorithm complexity is still important, but so is everything else as well. We've got the network and database, the things I was talking about before, the network and database performance, garbage collection, resource contention. But now you kind of knew about these. Now I want to put a new element into the mix of how you think about performance, and that is caching. So the conclusion is, well, actually, even though despite the title of the talk, it actually really is still your father's complexity. It's just more complicated than it was before. You're welcome to stay for questions. I'm happy if you want to. But I mean, I'm obviously over time. What to do? So all right. So the question is what to do. Well, yeah, it's a very good question. So what to do is try to organize your data. If you're using the Java Collections Framework, think about this. Try to organize your data to both to minimize the size of it and to improve data locality. That is the single takeaway that I would give you most. If that isn't going to work for you, I mean, do measurements, and if you find that your problem is the stuff I've been talking about here, look at one of these other frameworks.